Okay, so now we're going to look at an example of work. We'll use sort of the simplest sort of thing you can use as an example, which is maybe you pushing a box over some distance. So it's going to be a 100-pound box. So it's probably not quite that big. I'm going to push it 20 feet. And you're going to go at a constant speed, and there's going to be a 30-pound force resisting you. Okay. Okay, so now if there's or that's the force that you're pushing with. Okay, so that's 30 pounds here. Okay, so first we want to figure out how much work you do, right? So that's the work done by you, and that's going to have to be equal to the force times the distance, right? This is just the work done by you, so we've already got that. That's 30 pounds pounds of force, so we have 30 pounds of force, and you're going to push it 20 feet. So that's 30 by 20, that's 600. That's 600 foot-pounds. Okay, and that's a unit of work in imperial units, is foot-pounds. In, I need to remember to put the borders on this. In the metric units, it's Newton meters. All right, so that's the first part there. Next, we want the total work done on the box. Okay, the total work done on the box. So that's the work done, right? Which is the net force. Well, it's a constant speed. If it's a constant speed, what is the net force? 0. So we have 0 pounds of force here over 20 feet, which means that you have 0 foot-pounds. Okay, so when you have no net force, then you don't have any work. Now, again, you are doing the 600 foot-pounds of work over that distance, right? So you are doing work, but there's no work done to the object, no net work, total work done to the object, because while you're pushing this way with your force, there's something else pushing back this way with its force, and that's canceling out. So positive work, negative work. And that's the work done by the floor. So let's look at the work done by the floor. Right, well, how do we figure that out? Well, remember, yeah, W equals W1 plus W2 plus dot, dot, dot. So the total force, W, is equal to the work done by the floor plus the work done by you. That's everything that's doing stuff. We said that the total force was 0, so the work was 0, so we have 0 foot-pounds is equal to what we want, W floor, plus the work you do, which is 600 foot-pounds. So then we just solve for the W floor, which is equal to, we have to subtract 600 foot-pounds by both sides, which is equal to minus 600 foot-pounds. Okay, so minus 600 foot-pounds. All right, which I screwed up. So minus 600 foot-pounds there. So what we saw here was first how to calculate the work. In this case, the work done by a single force that's provided by you. So this force F is provided by you on the box. But we care about what's going on with the box, and we're labeling this by the source of that force, which is you. That's 30 foot-pounds times the distance, 20 feet. So W equals FD right there. Okay, that's good. That's not what we're going to use in most calculations. Most calculations we're going to use this, which is the net force, and we found that by saying, well, if it's got a constant speed here, then the net force is 0, so your total force is 0. So total force is that, and because we have V equals constant, we have no work, no net work, total work. And then we used this again, this sum, so that we didn't have to do this multiplication again. We just said, okay, well, we know that there's no net force on the box. We know that you are providing 600 foot-pounds, and therefore the floor has to cancel that out, so it provided minus 600 foot-pounds. And that's what we got for this particular problem. All right. So next we're going to see how that relates to motion, how that relates to the speed of an object before and after the application of a force. And after that, we'll talk about temperature. All right. Bye now.